Good morning, everyone. It's a pleasure to give you this presentation jointly with Dr. Yash Puranik. My name is Aphrodite Kishi, and I am the Director of Operations at the optimization firm, the company who've made the Barron Solver and the Alamo modeling tool. This presentation will discuss the recent advancements in the Barron Solver. It's organized roughly into three parts. I'll briefly introduce the company, and then Yash will discuss the Barron Solver and its major developments and performance improvements. Then he'll talk about the latest Barron software version that was just released on October 16th of this year. He'll discuss its new features and performance enhancements, along with performance profiles and comparisons, with some interesting concrete applications of Barron in industry, including a recent application for COVID-19 management. Lastly, we'll provide some demos using Barron, as well as some information on getting started with the Barron software. So what is the optimization firm? Well, Dr. Nick Sahinidis, when he was a professor at the University of Illinois at Urbana-Champaign, started the Barron project in 1991 with the idea of building global optimization technologies like the Barron software that provide cutting-edge performance for solving nonlinear and mixed integer problems. He founded the optimization firm in 2001 to provide Barron in the public domain. The Barron software has found many applications in current research areas, including energy optimization, process design, product design, and logistics and optimization. And today, the company has worldwide developers and more than 1,000 customers globally. We currently have a team of 8, but the people primarily responsible for the software's commercialization are, of course, Professor Nick Sahinidis, our co-founder and CEO. We also have Dr. Yash Puranik, an optimization research scientist, and myself, who works on day-to-day operations. Dr. Sahinidis is one of the world's leading experts in global optimization and mixed integer nonlinear programming. During his 20-year role at the optimization firm, Dr. Sahinidis has worked as a full-time professor of chemical engineering and industrial engineering, and has published numerous papers in the fields of mathematical programming and process systems engineering. From 1991 to 2007, he worked as a professor at the University of Illinois, Urbana-Champaign, before joining Carnegie Mellon University in 2007, and most recently Georgia Tech in 2020. Dr. Sahinidis has won numerous awards. He is a fellow of Informs and AICHE, and is the editor-in-chief of Optimization and Engineering. Our optimization research scientist, Dr. Yash Puranik, who you will hear from today, studied chemical engineering at Carnegie Mellon University and obtained his PhD under the supervision of Professor Nick Sahinidis in 2016. Dr. Puranik's work combined operations research, computer science, and engineering while emphasizing practical applications and developing novel optimization models. Since 2019, he has advanced both the Barron and Alamo software and developed efficient parallel algorithms for electric grid optimization at the optimization firm. So the company's key motivation and the key motivation of this presentation are that global optimization tools have significantly affected society over the past few decades and are needed across numerous business functions. So at the optimization firm, Barron is our flagship product that is a result of 30 years of research. It is a global optimization solver that implements a branch and reduce algorithm to solve mixed integer nonlinear optimization problems, MINLPs. Our developers worldwide are continually advancing the Barron project, and on average have doubled MINLP performance with each major Barron release since its launch, keeping Barron at the top of MINLP solvers. In 2018, the company introduced Alamo for automated learning of algebraic models. The Alamo software is a modeling tool that allows anyone to build algebraic models from data and first principles while ensuring that they are accurate and as simple as possible. Alamo is currently the only software capable of imposing physical constraints on machine learning models, enabling users to build accurate models from small data sets. Alamo was the focus of a $100 million DOE program that involved 5 DOE national labs and won a 2016 R&D 100 award. Since its introduction in 2018, Alamo has been used by hundreds of engineers and data scientists in industries including automation, chemicals, and pharmaceuticals. We have users from more than 100 universities and over 30 companies who are turning data into real insights with Alamo. If you're interested in learning more about Alamo, please attend our 30-minute technology tutorial today that will be live from our booth at 2:35. And with that, I will turn it over to Dr. Yash Pranik.
Thanks, Aphrodite. Just a quick note, if any of you have any questions, feel free to post them on the chat window. I think Aphrodite will be monitoring the chat window and will make sure to interrupt me as necessary. Also, thanks all of you for joining this workshop. I know we're dealing with a pandemic and still figuring out how to deal with an online conference. I appreciate all of you making it, whether it's early in the morning, afternoon, or evening, wherever you're all joining from. So, as Aphrodite indicated, I'm an optimization research scientist, and the company is called the Optimization Firm. So it's obvious we have a thing or two to do with optimization. I think the problem of optimization is as old as humanity itself. As long as we've had to choose from between multiple options and try to optimize a certain objective, whether that's minimizing the risk from predators or maximizing the chances of finding food, we've had to solve optimization problems. In fact, some of the algorithms that we use today have been known for over 100 years. In fact, Cauchy suggested gradient descent in 1857. I like to think of gradient descent as a ball rolling down a hill. So, if you think of your optimization problem as a landscape with hills and valleys, and say you drop a ball at some point, the ball will automatically follow in the direction of the hill or in the direction of the gradient and come to rest at some local point, and that's some flat point, in fact, and that's your local minima. Gradient descent, or in general what I would like call local search algorithms, have nice convergence properties, again, which has been known for a long time. The challenge comes in when we have non-convexities or combinatorics in our model, where it's quite possible that we might have multiple such valleys in our landscape. And if any of us have gone hiking or looked around us, we know that that's what the real world is like. In that scenario, where the ball comes to rest is a strong function of where you began your search. So, for instance, in the figure on my screen, if we had rolled the ball at some point on the left side, it's quite likely that the ball would have come to rest at the valley on the left, and we can see visually that that's the better or the global solution. So non-convexity is what causes the limitation in the abilities of local search, necessitating what we consider global search algorithms. That leads us to Barron. In fact, Barron was the first commercial code available that could solve non-convex, non-linear programming problems. And, as Aphrodite mentioned, even after 30 years, after a number of competitors coming into the market, it's still one of the best, if not the best. Uh, Barren is loosely based on the framework that's called branch and bound or divide and conquer. Again, that's not unique to optimization. Divide and conquer has been used in a number of different domains uh, for a long time. Uh, in fact, even for optimization, branch and bound was first proposed as early as the 1960s. I think where Barron really took off was that it was one of the first solvers that could do this efficiently. In fact, it was the first solver that could do this efficiently. If you go back to thinking about my example of optimization as rolling a ball down a hill, well, if you just roll multiple balls down the hill, I'm sure at some point you would find the global solution. And maybe in a way, that's what branch and bound does. But uh, to make sure you get deterministic guarantees, to make sure that you efficiently find the global optimum, you can't just be, you know, throwing balls around wherever you feel like. So that's what the branch and bound with Barron actually does with its strong set of convex relaxations, with smart branching and bounding rules and cutting planes and so on. Barron is able to do this efficiently. That's what makes it one of the best solvers currently. Uh, of course, to do this over a period of 30 years, it has taken quite a decent amount of theoretical advances, algorithmic ingenuity, and so on. And in that context, especially in Nick's group, we've been advancing the field significantly, right from say the early 90s when they introduced the idea of factorable relaxations, which was introducing a new variable and a new equation for every nonlinear functional form in the model. And the beauty of that technique is that it allows creating a convex relaxation in general for any functional form composed of factorable terms. From then on, the theories of say new novel range reduction techniques or convex extensions or even convexity detection and so on and so forth, we've been continuously pushing the boundaries of the field. Of course, if you go to next Google Scholar page, you'll see probably hundreds of articles around Byron. Nick's also written a book a few years ago, and I think that's personally what I find attractive about working for the optimization firm. All of our algorithms, all of our theoretical ideas, they're all published in literature. We do not believe in guarding our intellectual property in that sense. We believe in maintaining a competitive advantage by continuously innovating and by relying on the strength of our implementations. So again, any of the ideas I discussed now, they've all been published. You can find an appropriate reference for them. Uh, I think most of us must be familiar that, although the world is non-linear, non-convex, we often simplify it to make sure we can solve our problems. So, in fact, for the longest time, the only optimization problems that were being solved were linear. And more recently, I think the overall the community has turned towards solving mixed integer programming a lot more frequently since solvers in that domain have made tremendous progress. I think we're seeing a similar uptick in the use of nonlinear programming as people realize that the approximations made by linear models are not sufficient, or that there's value to be gained uh, by actually modeling all the nonlinearities as they exist or as they might exist in the real world. And this figure gives us some indication of that. I'm showing statistics here of the optimization problems that were solved with Barron via the NEOS server. So the NEOS server is an optimization service that's maintained by the University of Wisconsin in Madison. And anybody can submit a model right now and request a solution from a solver of their choice. So if any of you would like to try Barron, for instance, this is one way of trying Barron without having to purchase a commercial license. And we have some stats for the number of problems users have been solving uh, with Barron on the NEOS server. And you can see now that in 2019, that number has shot up to 200,000, and we might expect even more in this calendar year. So this makes me optimistic that people are finally realizing the value of nonlinear, non-convex programming and are turning their attention towards this field. As Aphrodite mentioned, we've been more or less doubling MNLP performance with every major release. And uh, of course, the way we've been doing that has been through a lot of theoretical and algorithmic advances. This is just a brief history of some of the major advances in the BARN project. So BARN stands for Branch and Reduce Optimization Navigator. Clearly, the fact that reduces in the name implies that we consider domain reduction techniques to be uh, very important for Barron. And in fact, those were some of the earliest advances or techniques developed by by us. So in fact, uh, the first set of advances we made were by proposing new range reduction techniques. Uh, Now they're fairly common and used pretty much in all solvers, but things like duality-based range reduction or constraint propagation for nonlinear programming were fairly new at the time. Um, I think the use of polyhedral relaxations was one big step that tremendously helped increase the robustness of Barron. So until the time, it was common for global solvers to try and uh, build convex relaxations for MINLP problems, which were typically nonlinear, and solve them with a nonlinear solver or a local solver. And the issue with that is that nonlinear solvers often tend to fail more frequently than linear solvers. And that is that is due to no fault of the nonlinear solvers as a whole. It's just that nonlinear optimization is more prone to failures. It's more prone to numerical errors. It's more prone to convergence issues. And as compared to that, if we look at linear solvers, they had been undergoing development for a lot longer. So the performance was very efficient, it was robust. So at that point, Barron decided to or implemented polyhedral relaxations in Barron. And the idea was once you have a convex relaxation for a non-convex model, you don't actually solve the convex relaxation to find your lower bound, but you further outer approximate it with hyperplanes and solve the linear relaxation. And of course, at that point, we are sacrificing some strength in our convex relaxation because we're taking the relaxation and relaxing it further. But this loss was more than made up for by the increased efficiency and robustness that we got from linear solvers. And that's so that was the next major stage of development where we implemented polyhedral relaxations, where we added links to cplex and so on. Again, something that was novel at the time is has now more or less been adopted by all our competitors, and I think most of them, if not all, use polyhedral relaxations for bounding. I think the next major stage of development was considering a more general or going more into more details of how you develop convex relaxations. So of course, factor programming, where you take any nonlinear functional form and introduce a new variable to replace it, is great as a general tool to find convex relaxations for any problem that's factorable. Although that's very helpful in general, often these relaxations are not the strongest. In fact, I think it can be intuitively obvious to everyone that if you uh, consider multiple functional terms at once, or if you consider multiple constraints at once, it might be possible to gain more information and build stronger convex relaxations. And that is what we focused on for a while. So a lot of the research work done at the time was around building convex relaxations for say multilinear terms, where you're not just considering say a term that says x times y, but you might be considering x times y times c times a times b times c, for instance, and build a convex relaxation for the entire term at once, or going beyond just single variable relaxations and going into multiple variable relaxations and so on. And that was the next stage of development in a way which, strengthened the convex relaxations and strengthened the bounding procedures in Barron. Um, as much as I talked about the strength of polyhedral relaxations and its improvement in efficiency, we revisited that topic in 2014. So, nonlinear solvers at that point had 10 more years of research, 10 more years of development, 10 more years of making sure that the solver is more robust. And at that point, we thought, we may not always need to outer approximate our convex relaxations. It might be possible to solve the NLP problems directly and still get the same level of efficiency and robustness that we were able to get with polyhedral relaxations. And with some experimentation, we eventually came up with a smart hybrid strategy where uh, Barron internally within its search automatically decides when to choose linear solvers or when to choose polyhedral relaxations and when to choose NLP relaxations. And in that context, why just solve LP relaxations? Also solve MIP relaxations depending on the particular problem, depending on the success rate of each of these relaxations so far in the search space. So that was another major step. At that point, we also introduced some cutting planes associated with integrality, things like click cuts or knapsack cuts, and so on. Uh, at that point, another major development that I was personally involved with was with infeasibility analysis. So, of course, this was personal to me because I was trying to solve an application that Barron consistently returned as infeasible. Uh, it was good to know that the model was infeasible, but that wasn't very satisfying because I didn't know what the issue was. I didn't know if it was a mistake I made in the model. I didn't know if it was the system itself that we were trying to ask too much from. Um, and at that point, we realized that this is a problem that probably a lot of practitioners face regularly in their work, where they might be trying to solve a model and the model is returned as infeasible and they don't know what to do about it. So at that point, we looked systematically at infeasibility diagnosis methods within Barron, and that that led to the uh, implementation of a module for diagnosis of, for the isolation of what are known as irreducible inconsistent sets. I have a small demo for that later in the presentation, and I feel like that's something that's practically very useful for all practitioners. Uh, some of the other developments more recently include, things like improved automatic differentiation, and of course, I think all of us here must know that first and second derivatives are very important overall for optimization, and being able to generate them efficiently is definitely useful. We also at that point proposed some novel reduction techniques that utilized first order optimality conditions or the first order Tucker conditions as they're called, and implicitly carrying out range reduction on them to achieve better performance. More recently, we've continued work on some stronger quadratic relaxations for quadratic problems or quadratically constrained problems, the so-called spectral relaxations and other techniques in this process. And as I promised, all of the things I've mentioned here, you can find appropriate references for them in the literature. Of course, leaving out things purely associated with software development, like the compressed data storage or data reversal and so on. Of course, all of this work has led to consistent improvement in Barron's performance. So here I have the results of different versions of Barron on problems in the MINLP lib. So of course, this is a standard test library of mixed integer nonlinear programming problems, and it has problems of various sizes. Some are extremely small with one constraint or maybe one discrete variable, and some of the largest ones have hundreds of thousands of constraints and variables. And the results here are plotted in terms of a performance profile. So with the help of the paver tool. So for those of you who may not be familiar with the performance profiles, let me see if I can actually use my pointer here. All right. I don't know if you guys can see my pointer. I hope you can. I'm just going to assume you can and keep going. So the performance profile, for instance, if we take any point on the profile, let's just say we take this point, what this is saying is that the 2019 version can solve 70% of the problems if we give it a time that's almost twice as the time that it takes for the fastest solver. So if you look at the leftmost point, we get the leftmost axis, the y-axis, we get an idea of how many problems are solved the fastest by any version. And if we look at the axis on the right, at the time factor as 1,000, we see that get an indication of the number of problems that a particular version can solve if it's given, let's just say, infinite time for the purposes of discussion. Um, so this kind of gives us an idea of relative performance of each of the different solvers in on this test lib. So we can see that back in 2001, we could barely solve maybe 20% of the problems, and uh, now in 2020 we can solve more than 80% of the problems in MNLP lib. And all these tests were run on the same hardware platform with a time limit of 500 seconds. So of course, it's tremendous progress to be able to solve as many problems in 8 minutes in 2020. That's a lot more than 2001. We're also much faster in solving these problems. So this gives an indication of the amount of progress we've made since 2001. Uh, Looking at the same analysis slightly differently, again, this is a plot that was generated with Paver, the Paver tool again, but the second version of Paver, Paver 2.0. And what this is plotting is the arithmetic mean of the ratio of the time it took Barron to solve a model versus the time it took Barron 2020, which is the current version, to solve the same model. So of course, for the reference version, Barron 2020, this figure is one. This number is one. And as compared to Barron 2001, we're 245 times faster today than we were 20 years ago. And obviously, I think all of you can agree that that's tremendous progress. Uh, the question we often get about this is that, of course, Barron relies on a lot of Barron relies on linear and nonlinear solvers in its during its search, and of course, all of them have made tremendous progress down the years. For instance, we know that Cplex, when Cplex releases its benchmarks, that they have made a tremendous amount of progress over the last 10, 20 years. So how do we know that this improvement is not from Cplex alone? So we did do some similar tests where we compared the performance of Cplex back in 2001 to today with the on the root node polyhedral relaxations that we solved. And of course, we noticed a significant improvement in Cplex's performance. And but our test showed that Cplex was about 5 times faster today than it was back in 2001 on the kind of problems we solved within Barron. So, even if we attribute, say, 5 times or 10 times improvement to improvement in the local solvers, a lot of the remaining improvement comes from improvements in the Barron score algorithm. Uh, of course, the figure of 245 was an average figure across the entire MNLP test set. But if we just compare 2020 across 2001, the version in 2001, we can see that Barron now is 10 times faster for at least 60% of the problems. And in fact, there are a large number of problems for which Barron in 2020 alone converges. And convergence is important in the sense that it gives you a definite proof of global optimality. Any of you might have worked with global optimization might have noticed that often these solvers like Barron will find the globally optimal solution very early in their search, but most of the time in global optimization is taking in branching and bounding and proving optimality. So in that sense, again, we've made a lot of progress in the last 20 years. One thing I find interesting is that there's still a small number of problems for which Barron in 2001 was slightly faster than Barron in 2020. And I think that's an indication that even back then we had a pretty good algorithm that wasn't as easy to beat. Um, I think given that we're supposed to go on for 2 hours and that it's going to be a long workshop, thought it would be nice to include a break time of 10 minutes. If any of you want to take a break, go get water, I think now is a good time to do that. I'll be here and Aphrodite will be here as well. So if you have any questions, if you have any comments, thoughts, now is a good time to mention them. It's 9:31 right now. We'll tentatively start again at 9:40. Just curious, how many of you have used Byron before, maybe in your work or for some academic exercise? Uh, Maybe you can just post in the chat window or use the raise hand feature in Zoom, maybe. So I see that Miguel has used Byron. Uh, so has John. Of course, there are a few of us here who have used Byron. John's been using Byron through Neos. That's awesome. So how many of those 200,000 problems were submitted by you, John? Few thousands. Very nice. Well, maybe we can encourage you to get a trial license for Byron and try it out locally on your machine. And among those who might have used Byron or any other global solver, how many of you routinely use it in your work for, say, practical or industrial applications as opposed to academic work? Anyone, or is it just me? Allison's mostly used it in academic work. Makes sense. Oh, Pablo, you used it for your work. I don't know if you're able to say a little more, but if you're, could you talk about in general what kind of applications you work on? You could unmute your mic and speak as well if you like. That's not a problem.
Hi, Yash.
Hey, how's it going?
I've tried for a few blending problems, for some nonlinear problems, but we have very big problems, so We don't really use it for the large instances, but for testing we do.
Makes sense. What's your experience been like? Any?
Sorry, what?
What's your experience been like with Baron? Mostly does well, fails for your problems, converges
Uh,
rapidly.
yeah, no, it's very useful for for getting bounds basically to know if you want to know how far you are from global optimum. That's very useful for the large problems.
Right. Miguel's also used it for his work. Miguel, what kind of work do you do with Baron?
Hi, can you hear me?
Yep.
So I've been using, well, not every day, obviously, but I've been using Baron for carbon capture applications, conceptual design, and superstructure optimization. Um, Minor bug in GAMS when you use the min function,
Mhm.
Baron will not accept that.
It's not a bug, I guess. It's a certain feature that we haven't implemented so far, but it's on the works. Just so you know, implementing things like min and max functions, uh, trigonometric functions, for instance. It's on the cards. Hopefully, we'll be able to release that new version out soon.
Yeah, I talked to Nick about that because I had quite a few, min functions, so I had to
Right,
reformulate everything.
right.
But
I
otherwise,
mean,
works perfect.
yeah. I mean, I know that I'm sure you know how to easily reformulate that min function as well, but of course it would be nice if Byron automatically does that. Absolutely.
The other feature that I don't know it exists. When the final solve is just the tip of the iceberg. So that's
Mhm.
when you want to find the global solution. But when you are debugging your model, is there something to speed up the solution or the results from Baron?
Uh, how do you mean exactly speed up?
So sometimes, well, in my experience, I will use Baron at the last run, and I will just Dicop or others, for the debugging process because sometimes Baron takes more time to start running.
Hmm.
I don't really think it's a bug or something. Baron starts working, implementing all the magic in the background, so it takes more
Right,
time. So I don't know if when you are debugging your model, which is most of the time you spend when you are modeling, right? So
right.
that waiting time is a little bit concerned.
Oh, I see. So, for instance, you just want to know real quick if we can find a feasible solution, for instance, or uh, things like along those lines. Is that what?
Yeah, yeah.
Oh, yeah, yeah. You can definitely do things like that. For instance, if you just set max iterations or max setter for Baron to 0, then Baron will only process the root node, for instance. Or if you just set things like there's an option called numlock, NUMLOC, which will just launch a number of different local searches within Baron, and that's that's also a good way because then at that point uh, you're just running local search with Baron, which is faster. And of course, you might say then why bother with Baron? Why not just use any other local solver outside? But you still get some advantages of using Baron. For instance, Baron will implement range reduction before it calls local searches. So, probably
I,
you're likely to get better solutions that way than if you just used something else directly.
I think that's the feature I was looking for. Thank you.
Okay, okay. But glad to be of help. Any other thoughts or issues with Baron anyone's faced? Well, since there are no more issues mentioned, I'm going to just assume that Baron's the best solver and Baron's perfect. Uh, it is 9:40, and I promised to get started again on uh, 9:40, so we can get started. Before we get started, a quick question to everyone. What interfaces do you typically use Baron in? Maybe you can post in the chat window, or if somebody would like to comment on an interface they use and they would like to see Baron being able to use, being able to access Baron through that interface. We have a vote for Pyomo. GAMS, AIMS, yes. I think the GAMS link to Baron is probably the oldest Baron link. Might be mistaken. I think that was the first Baron link. Again, GAMS and Pyomo. It looks like GAMS and Pyomo are the most popular. I think at some point there was also an interested audience among the Julia community. I guess I don't know if any of users of Byron through Jump are attending. All right, it doesn't look like there are any Julia users here, but that's okay. So yeah, I guess a good thing to mention again, Byron is available. You can use it directly through its modeling interface. You can also use it through other popular interfaces such as GAMS, AIMS, Ample, Pyomo, Julia, as well as MATLAB and YAML. So with that, let's get started again. I want to talk a little bit about the new Byron version that was released on October 16. That was released on October 16, and yeah, I think hopefully it's obvious to everyone by now how we would number our versions. So the version 2010-16 was released on October 16th, and this is not a major release. So this is still an incremental release, if you will, but we have a number of improvements in there. I think the most important one is faster automatic differentiation. So we've definitely reworked some of those routines that has improved the performance a lot, especially on problems that are not sparse. We've reworked some of the local search routines, as well as there are a lot of improvements in the cutting planes. All of that help in improving Baron's performance. Of course, there are bug reports and fixes from bugs and so on and so forth. I think there are a couple of new features. I think the one that's probably important for a lot of the audience is that we've turned on the process of returning duals. So by default now Baron will return duals, and uh, you know we obviously had facilities in place for calculating and returning duals for globally optimal solutions, but that was not turned on by default. And it seemed like based on the feedback we got from our users, I think the users like to see dual variables. They like the shadow costs or shadow prices for their analysis. So, keeping that in mind, listening to our users, we did turn on duals by default. At the same time, we also reworked how we do the calculation of duals. So, you can get primal and dual solutions as well now with the same performance with Byron. We also updated our links to some of the solvers. So, of course, Byron, the standalone version comes embedded with solvers like CLP, IPOpt, and we updated the link to CBC. So now Byron comes with CBC 2.10.5, and it also is able to link with the newest Cplex version. So, for instance, if you have access to a commercial Cplex license, or if you're an academic and you have access to an academic Cplex license, that's great. Baron will automatically find it and link to it, and you can use Cplex as the linear solver in your search if you need it. The previous Baron version before 2010-16 was released on April 14th. so 24-14. It was roughly a period of 6 months before the last release. So it's trying to compare the improvements that we've gotten in Barron's performance over the last 6 months. Uh, this is on a collection of about 7,000 nonlinear problems. So of course, this is not really an internal benchmark test, if you will, because this 7,000 set of test problems is a combination of publicly available libraries such as Global Lib and Princeton Lib and so on. So we've just combined everything together into one giant test library. And if you compare the arithmetic mean of the solver time, we take, again, just like before, we take 2010-16 as the reference version and compare, take the ratio of solution time with Barron versus the reference solver time. If we compare that figure, we can see now that the version 6 months from now is doing 20% better on average than the version 6 months ago. The improvements on again, a standard test library of mixed integer nonlinear problems is slightly better. In fact, again, I say this as an internal collection of 3,800 problems, but it's not really a private collection, if you will. We are just combining. I'm sorry. It's a combination of a number of publicly available test libraries, such as the MINLP lib, the IBM lib, and so on and so forth. The same statistic on this collection shows that we've actually made even stronger improvements on MINLP problems. So yeah, I guess that's an indication. Even within a period of 6 months, we're able to achieve a significant improvement, and that's just the process we've kept iterating for the last 30 years that allows Barron to achieve the level of performance it does today. So with that, I want to just talk about a couple of applications that we've come across in literature with Barron. So of course, as you all know, Barron is a general purpose nonlinear solver. It's designed to, a general purpose nonlinear mixed integer nonlinear solver. So it's designed for the solution of MINLP problems or NLP problems. But we don't have a specific application in mind, right? So it's not specifically customized for anything. Of course, we can think of a number of different applications where Barron can be utilized, but I think talking about those applications is limited by my exposure to things or my imagination. So I thought it would be a good idea to look at the literature and see where people might have used Barron for. And we found a number of different examples. Of course, there are examples in things like, I think Aphrodite earlier mentioned things like energy optimization or process synthesis or things like product design. I think some of those are I think some of the audience members can fairly see how Barron might apply there. We also found a couple of very interesting applications. I think one of them is COVID-19 management. And COVID-19 is definitely taking a lot of our brain space right now, all of us, the world, in fact. I think most of us are lucky that, we're able to do this conference online, we're healthy, but there are many jobs where that might not be possible. So this particular paper that just came out this year actually was trying to look at how we can control the spread of COVID-19. And I think, of course, when you think of words like control, I think the authors immediately thought maybe we can use model predictive control for COVID-19 management. And that's kind of what they did. They modeled the whole problem as a nonlinear model predictive control problem. They also designed a state observer. So I think for those of you who are familiar with control theory, of course, you need measurements to decide what your control action should be. And these measurements are not always available, or it might not even be possible to measure, at which point you often use things that are called as observers or state estimators, where you try to estimate the measurement that you need, which you don't have, with whatever else you have. Of course, managing COVID-19 is complicated. There are a number of different control actions you can take. They all have their challenges and all have their advantages, and the authors modeled all of those using logic constraints. So of course, now when you see logic constraints, you can see where I'm going with this. It's already a nonlinear model predictive control problem. You add logic constraints, which means you're now adding integer variables. The resulting problem was an MNLP. And the authors used Barron to solve the non-convex MNLP problem, and they were actually able to generate very useful insights. And in fact, some of the recommendations they came with were actual responses that governments utilized to try and manage the spread of COVID-19. So this I thought was a very interesting example where Barron was used, which I don't think I would have imagined or anticipated uh, without reading about it. Another interesting application we came across that we came across this year was around aircraft deconfliction, and we know that I'm sure all of us have flown at some point, and when when airlines are flying, you want to make sure that two airplanes don't come too close to each other. That's obviously very risky, and uh, to try and make sure that there's a certain minimum distance maintained between different aircrafts in air is the problem of aircraft deconfliction. Uh, Currently, it's solved manually by human air traffic controllers, and of course, they do a phenomenal job, because if we consider the number of flights that were flying in pre-COVID times, and the amount of uh, the amount of transport that was happening through airplanes, and you can imagine the number of problems that these air traffic controllers need to solve and how fast they need to solve to make sure they keep everyone safe. That said, of course, I think all of us can see the value in automating some of this process to, maybe increase the safety, reduce some of the burden on the air traffic controllers, maybe make their jobs a little easier. So the authors of this work, they formulated this aircraft deconfliction problem as a polynomial programming problem. Of course, once you have a non-convex nonlinear problem, you can try solving it with Barron, and that's exactly what they did. And in fact, they found that using Barron, they were able to find better solutions for certain problems in the literature than by using other methods that are more commonly used in this field. So again, another interesting example of how Barron was applied in practice that maybe I would not have foreseen. I think the last example I have for all of you today is around disposal of spent nuclear fuel. And this is an example that comes from Finland, I believe. So of course, whenever you have nuclear plants, I think there's the important problem of making sure that you dispose of the nuclear material safely. Because you obviously want to make sure that the material is cooled down, it has no longer uh, high radiation so as to harm the environment or life around. At the same time, you want to do it safely, you want to do it efficiently. You don't want to dispose of nuclear material too soon. You don't want to dispose it off too late. So I can see it's clearly maybe a scheduling problem or a planning problem, depending on the horizon you're looking at. So the authors looked at this problem of figuring out an optimal schedule for how to dispose of nuclear fuel. And of course, it was a large mixed integer nonlinear programming problem. There were several considerations to take into account, several safety constraints and economic constraints, and so on. In their work, they specifically used the conditions in Finland, or the case or a case study in Finland, and they were able to find robust solutions for their problem using Byron. And they go on to develop a nice interactive tool which can actually be used by the operators or the controllers to decide how to exactly go about managing the schedule. So again, another example of where Byron was utilized, which I would not have necessarily thought about. There are a number of different examples which you can find. If you just go on Google Scholar and look at and try to look at the papers that are citing Byron, I think you'll find a number of different and very interesting applications where Byron has already been employed. Uh, Next, I have a small video demo for all of you. This demo is around the infeasibility analysis tool with Barron. And as I mentioned, often, or I think what Miguel mentioned too, most of the time he spends is in debugging a model. And oftentimes we make mistakes in the model. They are infeasible. We copy something incorrectly, or maybe sometimes it's just that the system itself is infeasible, and we want to know more. We want to know what's going on or what we can do to fix the model. So this is the kind of situation where Barron's IIS isolation tool can be helpful. So I have a short video that talks about this isolation tool. Let me just pull it up. Sorry, let me pull it up on the right screen. You'd think I would know by now how to move a video across screens. There you go. All right, can everyone see the video that I'm sharing now? Oh, great, perfect. Let's play it now. Okay, can you folks not hear the audio? Let me see if increasing the audio helps. Is this better? All right. How about I just go on narrating the video with the as long as you can see the screen. So maybe I'll just do a live voiceover. It's unfortunate I had recorded this in advance just to try and avoid issues like these. I guess my plan didn't quite work out, but in any case, I'll just go on with a live voiceover. So sorry, just give me 1 second here. All right, so let's get started now. So this video I'm trying to demonstrate or try out the infeasibility analysis capabilities within Barron, just like we were discussing before, or what Miguel discussed, that our optimization models are often infeasible, and it's useful to know that our optimization models are infeasible, but I think we usually want to know more. We want to know what is causing the infeasibility. We want to know if it's a mistake in the model or if there's something in the underlying system. So to that effect, identifying what's known as an irreducible inconsistent set, also known as an IIS, can be very helpful. That's what this video is primarily trying to show here. I think some of the users are already familiar with Barron in the many environments, including GAMS, AIMS, and so on and so forth. But for this demo, I'm just directly using Byron through its own modeling language. So the example that I've used here is the one of the classic examples from textbook. I think it's called the Himmelblau problem. It just has 5 variables, with lower and upper bounds and 6 constraints. And I think looking at this the screen, I think it should be fairly obvious how to use Barron's modeling language, right? We have a number of obvious keywords such as lower bounds and upper bounds and so on and so forth. Uh, we have 6 constraints here in this model, and I'm just solving it with Byron. And of course, since it's such a tiny problem, it solves immediately on my computer. Now, what I'm going to do is I'm going to introduce a mistake in the model. And I mean, of course, since I'm doing it artificially here, I know the mistake I'm making. But uh, if you notice on line 27, I replaced the addition sign with a product sign on there. Now, if I run the model again, this model is infeasible. Of course, knowing it's infeasible is helpful, but I really want to know what caused the infeasibility. In fact, this can be problematic if we have really large models with, say, millions of variables or constraints. It's not easy or even possible to actually manually go and look at every single constraint. Things might be even worse if the issues are with the parameter values and don't have easy ways of knowing or checking or verifying all the different parameter values in a model. So to do this, you can to try and maybe help in identification of causes of infeasibility. You can use Barron's IIS isolation module or routine. You can invoke it by setting the option comp IIS suitably. That's what I've done here by setting comp IIS to 1. In fact, we have implemented a number of different algorithms within this IIS isolation module, and there are 4 main algorithms, and there's a fast heuristic. Of course, more information about that can be obtained from the manual. So I'm not going into too many details right now. So let's just see what happens again if we run this model, which should be happening any second now. Right. So when I run this model again, of course, Byron will not take my word for it when I invoke comp IIS that the model is feasible, that the model is infeasible. It will still try to solve it. After the initial search, when Byron confirms that the model is infeasible, it goes on to the calculation of an IIS. So let me just pause here for a sec. If you can see, the logs indicate that we're now calculating an IIS, and there are some other messages about the IIS. It contains 1 row and 3 columns. So the results for what constraints and variables are a part of the IIS is actually a part of the Barron's results file, which when you're using Barron's default interface, the file is called res.lst. So that's the file that I'm now going to open with my favorite text editor, which is Vim. So in this file, I have a listing of which constraints and variables are a part of the IIS. And the module has identified equation 2 as a problematic equation along with certain lower bounds. And this is important because I know that we know this for a fact that we introduced a mistake in equation 2, and that is kind of a problem. But since Barron is a general purpose modeling language, Barron does not know a priori or since Barron is a general purpose solver, Barron does not know a priori what the intent of the modeler was. You could resolve your infeasibility either by changing equation 2 or correcting it, or you could also resolve your infeasibility by updating bounds on each of the variables. If you further reduce the lower bounds for x1 or x2 or x5, you might still be able to find a feasible solution. So since we do not know the application, we cannot determine a priori what the resolution is. But the idea is, since we found an IIS that is smaller than the original model, now hopefully it's easier for you as the modeler to go look at a very small part of the model, and this might be even more important if you're dealing with very large models. So of course, you can find more details about this in the corresponding paper that I'm citing here. And we did a lot of computational analysis in this paper, and in fact, we did find that for many problems, especially some of the largest problems, the IIS returned was often much smaller in size as compared to the original size of the models. So that kind of helps focus your attention uh, on a specific part of the model and hopefully speeds up the debugging process. Uh, are there any questions for me at this point? Okay, since it doesn't look like there are any more questions, I'll go on to the next demo video I had planned, and I believe we'll end up with the same issue of video audio. So I'm going to do a live voiceover as I play the video. So bear with me. All right. So uh, this was a short video basically to try and look at the importance of range reduction techniques within Barron. So in fact, Barron, as I said before, Barron stands for Branch and Reduce Optimization Navigator. Clearly, we think Barron's range reduction techniques are very, very important. So I just have a quick short video of demonstrating its importance. For this example, I'm using the Barron's interface through Python, made available through Pyomo. Uh, of course, Barron is also available through CAMS, MATLAB, AIMSample, and so on. The problem being considered here is the uh, I think it's called the BRYBNT problem. It's from the CUTE test set, which stands for Constrained and Unconstrained Test Problem Set. I think the application of this problem is modeling is basically trying to find a solution to the system of nonlinear equations, uh, but instead of formulating it as a problem for finding solutions to a system of equations, it's been formulated as a least squares problem where we're trying to minimize the violation of each of the equations in the system. So of course, if there exists a feasible solution to the system of equations, the optimal objective will be zero. Since it's a system of equations, we don't really have any constraints in this context, and none of the variables have any bounds either. Of course, I think all of us know that not having any bounds is a challenge. Now, when I talked about a branch and bound kind of algorithm as exhaustively looking at a landscape, it's obvious, a larger landscape is going to make it harder for uh, a global optimization problem. And in fact, in this example, we have no bounds. The domain is infinite. So you'd expect that this problem Barron's, it's harder for global search in general. But if we run this with Barron, which I should be about to do in a couple of seconds, we'll see that, let's see. All right, so when I solve this with Barron, I call it directly through Pyomo, through its Pyomo link. See that Barron was able to solve this problem very, very quickly in a matter of a couple of seconds after Pyomo created the model. So that's great. And the main reason we're able to do this is because of the range reduction techniques that are implemented in Barron. So let's see what happens if we turn some of these techniques off. That's what I'll do next. There you go. So that's what I've done by adding these options LBTT2, OBTT2, T2, M2, and B2. I've set them to 0 while invoking Barron. And what they do is they turn off all the range reduction techniques in Barron. So LBTT2 stands for linearity-based bound tightening, and that's kind of that's the constraint propagation algorithm in a way for range reduction for linear constraints. OBTT2 carries out range reduction using optimality arguments. There are similar other range reduction techniques that rely on duality-based arguments or non-linearity-based arguments and so on. And you can imagine that now, if I've turned them on, now Baron is going to have a slightly harder time to solve this model. And that's kind of exactly what happens. I think this is now going to take at least a couple of minutes before Baron is able to solve the model. So again, same model, Baron is able to solve them, but with range reduction techniques, we could do it in a couple of seconds. Without range reduction technique, the whole process took a couple of minutes. So hopefully this uh, conveys the importance of range reduction techniques for Baron. Again, just wondering if there are any questions for me or any thoughts or comments. Just curious, has anyone used the IIS module in Baron before? All right. So John and Brian both say they haven't used it so far, but I hope you can see it might be valuable. If you do end up dealing with infeasibilities at some point, you can give that a shot. Just a couple of testimonials, if you like, citations again from papers that I have on the slide. And you know, these authors have again used Baron in their papers and have found it very useful. So the 2005 paper suggests that at the time Baron was the fastest and the most robust solver. It still is, of course, but the paper was from 2005. Uh, the paper from Ruth in 2005 was also interesting, where I think that was also a very interesting application where the author developed a new numerical method for uh, integrating differential equations, or for solving the system of differential equations, I think, if I'm not mistaken. And this new method was, no, I think it was a new Rangi method. Anyway, it was a new numerical method, and it was very interesting how the author formulated it as a global optimization problem and used Barrett to solve it. So it's just some citations again that we found from literature. Of course, Barron's the theoretical advances as well as algorithmic advances have been well recognized by now through a couple of different awards. So Barron, I think Barron won the Beale Orchard Hayes Prize back in 2004, I think, and as well as the Informs Computing Society Prize, and that's just a general recognition of the work we've been doing so far and the work that we continue to do. As a policy, as company policy, we do not release the names of any of our clients or customers. That might change in the future, but as of now, we don't do that. So instead, I'm just providing some aggregated information on the kind of industries or the kind of clients that we have that we know use Parent. And obviously, or unsurprisingly, things like oil and energy and chemicals are high on the list, but also interestingly, industries that belong in the computer software sector or the infotech sector have also found use for Baron in their work. And I think it just goes back to something I said before, where uh, since it's a general purpose solver, the kind of applications Baron can probably used for is that I can think of is limited by my exposure or my imagination. And I'm sure there are problems in every field that are non-convex, and that's where value can be attained by solving the full model instead of approximating it with linear models, for instance. And so I'm sure there are many other industries where Byron might find use. Just a quick stat on where some of our customers are located, and as you can see, they're located on all continents except Antarctica. We have a number of different we have a number of users all across the globe, across Europe and Asia and North and South America. There are more than 600 registered universities, so but as well as a number of different companies that are now using Barron, and we only hope that this number continues to grow. Uh, some of the top countries that have been using Barron include, well, not surprisingly, the US, since this is where it was developed and first released and so on. But more interestingly, there's also large user base in Asia, in China, and in India, for instance. And we often get requests for very interesting applications from some of these countries. So can only hope that this figure grows darker and darker as time goes on. So that's all I had for uh, all of you today. Uh, if there are any questions, I think we can answer them now. What do you think, Aphrodite? Is now a good time for another short break? Maybe just give everyone a breather.
I think so, yeah, because the next part is pretty much housekeeping and logistics on getting started with Barron licenses.
Right. So it's about 10:16 right now, so maybe we can get started at 10:25. And in the meanwhile, I'm here, Aphrodite is here, if there are any questions or thoughts or comments. While we wait on getting restarted, I'm just curious about uh, something I often faced in my work, and it's you might make a really nice optimization model, and uh, you might have a nice solution, and it looks really great on paper. But how many of you have actually had trouble convincing your management or your operators about uh, whether the solution will actually work? And do you have any interesting stories or strategies on how you go about convincing people of the value of optimization? Any thoughts, anyone? I think Pablo, you said you used it before for planning and scheduling. How was your work received in the company overall? Looks like Pablo is also taking a break, which makes sense since I asked him to take a break. Anyone else have any interesting stories to share?
This is Brian.
Hey, Brian.
Hi. I don't have any interesting stories to share, but I'm wondering if you have any experience solving AC optimal power flow using Baron.
So,
I have a few projects where we're either like comparing alternative form, either approximations or relaxations to AC optimal power flow, or trying to recover a good solution. Wondering if you have any insight, any suggestions.
right. So we actually did participate in the grid optimization competition last year, and we did spend a lot of time looking at AC optimal power flow problems. Uh, to be honest, I think it was one of the most challenging problems I have worked on, mainly primarily due to scale, but also just due to the nature of the problem. So I can understand your the difficulties you're facing there. In our experience with it, Baron did work very well, especially in finding good bounds. Of course, given the scale of the problem, finding globally optimal solutions or proving optimality took took some time. I think we found it very helpful to find good initialization, finding a good initial solution for the problem, and that was very helpful. I think another thing that is on the cards, and we haven't. That's something that we're working on at the moment is introducing trigonometric functions within Byron. So I think Miguel also asked for things like min-max functions that Byron does not currently accept, and of course, it's easier to reformulate min-max as opposed to reformulating trigonometric functions. So that is something that's definitely on the cards. So I mean, for now, you can definitely use the rectangular formulations for AC optimal power flow and try to use them. But I believe once trigonometric functions are also included in Baron, it might be easier for your problems. And I think, Brian, what I'm going to offer you next, I think it's an offer for everyone. If you have specific instances where you're having trouble, I think you're always welcome. If you can, I know it's not always possible, but you're welcome to share them with us. We're happy to look at them, figure out what's going on, and try to help you solve them faster and better.
That's great. Thank you for that offer. Back to the trig function, though. A bad idea to until you have trig functions implemented, just implementing a Taylor series approximation with say three, four terms. Depending on like what range of the domain one needs to cover. Do you see any possible issues coming up with doing that?
I personally don't. I haven't experimented with it, to be honest. So I was able to reformulate using rectangular formulations, the what's it called, the IV formulation, I think, and that worked fine for me. Uh, I might only be worried slightly about numerics when we use Taylor series approximations, and depending on how tight your feasible region is, you might run into issues, but it's definitely worth a shot.
Okay, and from your earlier comment, it sounds like, so I've heard that other approximations like the second order cone um, relaxation to AC, it often will find you an optimal solution, although it's not provably optimal for AC. So it sounds like from what your earlier comment, if you do have a solution that's good and close to optimal, then what can Baron tell you if you like try to initialize with that solution?
Right. I think firstly, with my experience with the problem, the DC approximations, for instance, or even some of the conic approximations did not give even a feasible solution for the full problem. So we definitely had challenges with that. But let's just say for your example, your approximations are able to find a very good solution. That helps Baron in the sense that now you have a very good upper bound, and overall that dramatically helps the search space. And it's quite possible that your approximation or your heuristic did find the global solution, but you do not have a proof for it. When you solve the problem with Baron and Baron terminates, you have a guaranteed proof of optimality. And depending on the application, that might be very important. If that makes any sense.
Yeah, that does make sense. Thank you.
Right. Of course. Are there any other questions based on the problems you have been solving or any other experiences you've had? Anyone? If not, I think I can hand it over to Aphrodite and we can get started again.
All right, thank you, Yash, and thank you everyone for participating in our workshop so far. I want to discuss a little bit about our licensing options before we go. If you want to try Baron, we're happy to provide free 30-day trial licenses for those wishing to try Baron for commercial purposes. And as a reminder, Baron can solve all major mathematical problem types, including problems for linear programming, nonlinear programming, mixed integer programming, and mixed integer nonlinear programming. So just email sales to request your evaluation license and we'll get you started. We also provide flexible licensing for perpetual licenses. All of our Baron licenses are perpetual and give you full access to the software with no restrictions on problem size and unlimited simultaneous uses. All of our licenses allow you to run Baron on any number of processors, operating systems, and computers for which Baron is available under any combination of MATLAB, YAML, JUMP, Pyomo, or Baron's native modeling language. Any single user can run multiple jobs on multiple machines. So if you have any more questions about our licensing, please feel free to reach out. Our pricing is transparent. It's listed on our website. These are the current prices for commercial users who use Baron in industrial and commercial activities at companies, national labs, and even universities. As you can see, we offer single user licenses, 10 user licenses, and site-wide licenses for unlimited users. We also support, of course, academics and academic research. And so we give academics 80% off all of our Barron licenses. These academic prices apply only for use in academic teaching and research activities at degree awarding institutions. All of these licenses come with full features and of course, no restrictions on problem size. We also offer complimentary licenses to the Center for Advanced Process Decision Making and individuals affiliated with Carnegie Mellon University, the University of Illinois at Urbana-Champaign, or the University System of Georgia. These licenses can be automatically generated from our website, and they come with unlimited renewals as well as maintenance and support. So due to high demand, we recently brought back consulting services. Our Barron developers are available to provide model development and tuning so that you get thoughtful, efficient solutions from people who have deep expertise with the Barron solver and can make recommendations for your various problems or business problems. You can email us at sales@minlp.com for any of your licensing or consulting needs. To those who attended Informs this year, we are currently offering free Barron maintenance on Barron licenses through the end of the year. If you already have a Barron license, you can get 3 months of free maintenance. And if you buy a new Barron license, you can get 6 months of free maintenance. This maintenance program gives you access to all software upgrades released during your maintenance period, as well as technical support with direct access to PhD level optimization experts like Yash. Just a little fun part of our workshop, just please enjoy our giveaway contest for a $100 Amazon gift card. This giveaway is for those who attended our Barron workshop. And also follow us on social media, whether Twitter, LinkedIn. Just email us your business card at info@minlp.com by this Thursday at 12 p.m. and we'll randomly select the winner and email you and announce them on social media. So we hope you take advantage of this. All right, thank you to all who attended our workshop and to everyone who has already used Barron or is hoping to use Barron in the future. Please feel free to contact us if you have any questions. We hope you're staying healthy and safe out there and have a wonderful rest of the conference.
We have a couple of questions on the chat room, so I thought I would take them now, if that's okay. So there's a question from Brian about what's the advantage of using Barron for solving MIPS, especially if you have a CPLEX license. And I think the short answer is it's a completely different solution process, if you will, because if you are solving a MIP and if you have a CPLEX license, it's not just straightforward as we just throw the same MIP to CPLEX and just give you back the solution. Barron takes control of the solution process, which means we maintain the branch and boundary, if you will. We add our cutting planes. We do a number of range reduction techniques and so on. And this is in addition to whatever techniques CPLEX might be using internally as well. So the solution process will look different. Now, whether that necessarily improves the solution performance on your problem or not, I think that depends on the particular problem. I'm sure MIP is NP complete or MNLP is NP hard, which means there's no single efficient algorithm that will work for all kinds of problems. The best way would be to try both and for your specific problems and see if Barron does add anything more. I think Miguel also added something about using, say, Barron with CPLEX versus Barron with, say, non-commercial MIP solvers. So you're basically saying Barron with CBC, right? And I think that the performance is, if you're only considering problems without integer variables, the performance is extremely close in our test sets. Cplex does give you some advantage over CPC if you have integer variables in your model. But again, the exact amounts of the advantage depend on the specific problems. It's quite likely that there are some problems where Baron with CPC will outperform Baron with Cplex. Some of those things are just, depend on the exact nature of your problem. And yeah, Miguel, it's not too late for questions at all. Please feel free to ask more questions if you have any. Brian, did I answer your question? Did you have any follow-ups to it?
No, that answers it. I think the answer is it's worth trying both approaches.
Right.
Okay, and you have similar comments for non-linear programs, purely continuous, say convex problems,
Okay.
using Baron versus like using IPOpt or using Nitro.
Right. So if you are solving purely convex problems, again, IPOpt, Nitro, they are guaranteed to give you the global solution, since local solution is global, and for those problems, of course, subject to their efficiencies and robustness. It might still be useful to try Baron, just because Baron might you might be able to take advantage of some of the range reduction and pre-processing techniques and so on. The other thing I want to highlight is that if you know your problem is convex, or if you know that your some constraints or functional forms in your problems are convex, you can pass that information to Baron using suitable options, and Baron will keep that in mind, right? And that helps speed up the process. So of course, Baron does have convexity detection too, so it will identify convexity if a problem is convex for many different kinds of problems, but it's quite possible that there are some that we don't identify, and in that case, you can let us know that a constraint or a model is convex, and you'll get advantage of all the range reduction and other things on top of the local search that you really need to find your solution. Does that make sense?
It does, and you and I have emailed before,
Yes.
and I believe you said that Baron uses 3 different nonlinear solvers kind of dynamically. Unless we have like other questions, would you mind like describing like how that works? I'm really curious.
Right. So when I say 3 nonlinear solvers, that's the direct link to Baron, if you will. So if you have access through Baron through GAMS, for instance, you might have access to more solvers like Minos or SNOP that come from GAMS, and Baron can use those links as well. But for this, let's just talk about the 3 solvers that come from the standalone version of Baron. Baron comes embedded with IPOpt, filter SQP, and filter ST. And the way we decide which solver to use is basically based on a learning algorithm, if you will. So initially, when you start a problem, you don't know anything. Maybe we pick one of the 3 solvers at random, or based on some initial bias that we might have assigned to each of the solvers. And then based on the success rates, and in this case, we can define success as the time it took to find the feasible solution, or in fact, sometimes one of these solvers might fail, and then you assign a negative score to that solver, if you will. So basically, based on these statistics, at some point, we get a fairly good idea of which solver is going to work better in the search process, and that's what we use more opportunistically. I can't remember the exact reference from the top of my head, but this algorithm has been published in the literature. So I think I have your email, Brian. I can share the reference with you. And it also has details on how we decide to switch between solving a linear relaxation versus a non-linear relaxation. So you can find all the details there.
Okay, thank you. And could using multiple cores possibly help?
Yes. So at the moment, Baron does have some support for multiple cores, but if you have, so basically at that point, if you're using Cplex or CBC, for instance, for solving relaxations, using the threads option in Baron, you can assign multiple cores for that solution process. We're also working on adding parallelization more in general. So, adding multiple cores is helpful today. It's going to be even more helpful tomorrow, maybe. Well, not exactly tomorrow, but in the coming near future. Of
Great, thank you.
course. Are there any other questions or comments or thoughts? I guess if there are no other questions or thoughts, maybe we can bring this workshop to a close. I guess we ended a few minutes early, but I'm sure all of you have a long day ahead listening to lots of workshops and presentations, and uh, hopefully you don't begrudge me these extra 19 minutes that I'm saving you. So thank you all again for joining this workshop. Thank you all for all your questions. And again, any questions, any comments, please email us at info@minlb.com. You can also go to the website and get all the information that you need. So thank you all and have a good conference.
Thank you. Bye.
Thanks, Miguel. Bye. Thanks, Sean. Happy to be help.
Thank you, everyone.
Thanks, Yash.
Thanks, Brian. I look forward to chatting more with you or email.
You as well. Thanks.
Thanks.